Nächste Challenge, nächster Pitch. Ja, genau, Andreas, Achtung, es ist euer Einstieg. Ich habe schon die Hand vom Andreas Mühlberger gesehen. Ich habe hier eine ganze Liste von Namen. Man könnte natürlich jetzt wieder ein Feuerwerk veranstalten, mit wem aller Infineon zusammengearbeitet hat. Viel wichtiger ist gleichzeitig, dass Infineon ein Wegbegleiter von der allerersten Stunde für Industry Meets Makers ist. Mit vielen wechselnden Personen. Wir haben ganz viele Personen in Infineon schon kennengelernt. Eines sei mir erlaubt, bevor ich an den Andreas übergebe, die Protagonisten von Infineon kurz vorzustellen. Andreas Mühlberger eben, Ronald Stärz, Andreas Albrecht und René Fabien de Montmorency. Andreas, das Wort gehört dir, die Bühne gehört dir. Ich denke, du führst uns jetzt durch deine Ergebnisse selbst durch. Stummschaltung aufheben, bitte.
Ja, sehr gerne.
Danke.
Ich teile nochmal meinen Schirm. So, very welcome also from our side. I hope you can see the presentation. We will do the presentation in English, and we are here in a room in Villach because we used also this bootcamp format yesterday already for a day to invite our university and school partners. We had yesterday a very intensive session where we used the time to really go into detail into all the technical discussions. We would definitely, when I would share with you all the details we discussed yesterday, you would definitely be bored because we really went into very much details about our PV optimizer and had a very, very good exchange. So here in the room, I have my colleagues from the University of Zagreb, which worked on the challenge in the room. We also have the colleagues from the University of Vienna, which Technical University of Vienna, which participated, the Technical University of Sofia in Bulgaria. Also, these people, I'm really happy that all of them drove to Villach, came to Austria, and joined us here in the finals. Yesterday, we also could welcome the HTL from Klagenfurt. Unfortunately, they cannot dial in today because they are in school at the moment. The same for the guys from Wolfsberg. They also, at the moment, HTL, the school in Wolfsberg, is also in the school. And we have online the team from Passau. The guys from Passau, from the university in Passau, started a bit later. And we had upfront the alignment where they decided, well, they are still working a little bit on the topic, so it doesn't make sense to join the on-site event in Villach, and they have dialed in. I already saw them here in the list. So to quickly summarize and get everybody on track, what we did, basically what we did is we wanted to optimize a solar panel. And this diagram here just shows you a solar panel has different performance parameters, for example, depending on the temperature. And as a consequence, we want now to keep this solar panel always in the optimum power point so that we get most of the electricity out of the solar panel whenever we operate it with high temperatures outside, low temperatures outside. Depending on all the environmental conditions, we really would like to get always the maximum power out of the panel. So we have supplied our teams with an electronic circuitry. And this electronic circuitry now helps to, on the one hand, optimize this power output. So putting this between the solar panel and the inverters will ensure that always the maximum power is supplied to the inverter, and we are saving and we are always operating in the best possible way. This was the electronics that we supplied to the guys, and we gave them a clear instruction that they will get the microcontroller boards, they will get the hardware, they will get a software framework, and then quite intensive work started for the teams to really start to develop a software algorithm, which is then running on this board that really leads to the operation of the solar panel in the optimum with the optimum power output. And the result now is really great. We had yesterday very intensive discussions showing the different algorithms, showing the different results, and discussing which kind of hurdles the people have solved. This was the timeline. We sent out the hardware to the guys. We had several Q&A sessions online where we brought the schools and all the university partners together, where they dialed in, gave a short status update, gave us short reporting. As said, yesterday we had a one-day workshop here in Villach, finalized with some nice dinner all together. And now I would, with that statement, hand over to the different teams and would ask them to present the results. And we would start with the team from the Technical University in Zagreb. We just need to switch to the right presentation now. I think I need to share again, right? It was lost now.
Yeah, you need to re-establish the sharing. Yeah, there we go.
Yeah, and
You're on.
Presentation mode, and I hand over.
So hello everyone, I am Lóránt, I'm from the University of Zagreb, and our team consists of 3 students and 3 professors. So that's me, Lóránt, we have Luka and another Lóránt, and our professors were Tomislav, Sandor and Marinko. And I will try to avoid any really technical stuff so everyone can follow. So basically the first step we did was we created a simulation of the entire board in software so that everybody could develop code and the algorithms remotely from home without having to be at the university on the board. So this helped us because we could really quickly change and test new things and also verify that when any problems arise, so that they were a result of the board or from the algorithm. And this on the left is our laboratory setup, and it's basically the same schematic as the one below. So the first step was to set up the board. So as you will see with other groups also, the biggest problem was the hardware limitations and the measurement noise. So one thing we did was, as you can see on the lower right, when the converter is switching, it creates electromagnetic interference, and if we measure at that time, it will disturb the measurement. So we created a triangular carrier wave, which would then trigger the measurements between 2 switchings, and this helped us reduce the noise. And also, to further reduce it, we took 4 measurements and took an average. And the next step was to identify solar panel. As you might have seen, it has a curve depending on the voltage. So in this top graph, you can see the curve that we measured. And the first step was to measure the curve. So we created a so-called sweep, which basically goes through the entire voltage of the board, of the entire voltage range, and it gets a map of the photovoltaic panel. And the first algorithm we used to keep the maximum point was a so-called perturb and observe. And the basic idea is, if you look on the top graph, on this curve, if we are on the left part, the voltage and the power are proportional, but on the right, they are reversely proportional. So we would increase the voltage until we reached that point, and then we reversed the step of the voltage. So we would go backwards. And in this way, we would constantly oscillate around the maximum point. However, because of the noise, this proved to be not so great because the point would not be tracked. It would drift all over the place. So the next step was to create something like an adaptive voltage change. So if we were near the optimum, we would try to reduce the change of the voltage. And if we were very far away, we would try to increase the change of the voltage to try to reach the maximum faster. But none of this actually helped because the noise was really troublesome. So at this point, we quit all these algorithmic approaches and went back to control theory. And we used a classic PI controller, which is used in 95% of all applications, to try to implement this adaptive step. However, that also did not work because this integration part was conflicting with the noise, and it created problems and also audible ticking of the board. So to fix it, we created a high pass controller, but it's actually really simple because the filter would kind of slow down the change of the noise, and then we would only act. So if the change of the power is very fast, we would create a really large step to try to suppress it. But if it was slow, we would try to keep it slow, so it would create a really slow step. And this proved to be the best solution. And as you will see on the next slide, the results are quite good. So yes, we tested it on a real solar panel and also on the lab, in the laboratory on some resistors, which was kind of a basic test. And we can see that all algorithms actually followed the maximum power point, but this MPPT V2 is really more stable. There are quite less oscillations. You can see these orange lines. They're very smooth. And this was the best result we could get. And on the top right, you can also see the power curves that we measured from the real solar panel. So this proved that the theory was spot on. So that's, yeah, verified everything. And this is our team. On the left, we are the students, some of us, and on the right are our professors. And thank you for your attention.
Thanks a lot for that. And that I would immediately switch over to the team of Vienna. The sharing is still in place.
Yes, so hello everyone. So we are from the TU in Vienna. I am together with my teammates, Andreas Zimmer and Philipp Pelzmann, and I myself am Tobias Wallner. And we kind of had the same problem. We had to find the maximum power point of solar panels. On the left, you can see the basic shape of the power output compared to the voltage. And in small circles, you see the power point. And one approach, kind of as mentioned in the presentation before, is that you stepwise move towards the maximum power point and see if you get more power output. And the moment you tip over the maximum power point, the power decreases, and then you step back and move back and forth in front of or above the maximum power point. Another approach, before that, we have also, you can see a lot of simulations here. So on the left, you see simulations that we did beforehand to see how the algorithm would perform. And then on the right, on the top, you can see measurement results. So what you see here is that the algorithm quite quickly finds the maximum power point. So it goes from the low to higher voltages relatively quickly. However, you have a lot of ripple noise due to the steps around the maximum power point. And on the bottom right, you see a small setup with the board, an oscilloscope, and a power source. And second algorithm that we also tried, it is a combination of applying an offset and an oscillation, a sine wave, to the panel, to the optimizer board. And what happens is, on the graph on the left, you can see when we apply a driving signal that's below to the left of the maximum power point, we have a positive gradient, and therefore the sine wave that we put in comes out in the same phase that we put it in. And if we are on the right side of the maximum power point, what happens is we have a negative gradient. This means that the modulated sine wave will flip, so it will have the negative sign, and then we will walk the other direction. So from this, we always know in which direction we need to walk in order to reach the maximum power point. And the detailed algorithm can be seen on the right. And this works quite well. We can also see some simulations. So on the top left, you see some simulations. And one thing that is really nice about that algorithm is that it starts out with large oscillations as seen in the top left diagram. And if time progresses, if we reach the maximum power point, the oscillations get smaller and smaller and smaller. We have less and less ripple the closer we are to the maximum. On the bottom, we also see a real-world test where you can see that we start on low voltages and slowly increase our way up to the maximum power point, and then we keep and stay tracked on the maximum power point. And this algorithm has the advantage that we always know on which side on the maximum power point we are, and it has also a very nice noise suppression. And here you see also a real-world setup. So the solar panel will be used to measure this and see if our algorithms work in the real world. And then you also see the graphs to the right of the solar panel, where you can see that the power output really depends on the voltage that you or the duty cycle that you use and that you operate in. And you can also see on the gray graph that there is one peak, and that is the peak that we would try to track. And both of our algorithms seem to track those peaks really well. Yes, thank you very much.
Good, thanks a lot. And then finally, we would also invite the team from Sofia to share their results. And before we then hand over to Passau.
Okay, hello everyone. My name is Kristiyan, and I will present our concept from the Technical University of Sofia. First of all, I want to thank all for the opportunity to work on such a challenge. It was really challenging, and we have learned a lot of things in the engineering process of creating a PV optimizer. So our team was consist of me and my mentors, Vladimir Dimitrov and Dimitar Nikolov. And what we have done, it was a fully functional PV optimizer. We have tested it, and I will try not to bring too much technical concepts because I know we will be bored. So first of all, we also started with a few simulations, but what we have found out that the simulation and the real world behavior of the PV optimizer are not really matching, because there are so much disturbance factors that you cannot simulate, and the simulation is not really close to the real world behavior of the device. So because of that, we had some problems with the board, and we needed to overcome this problem. So what we've done, because we could not repair the board, which was broken because the simulation and the real world example are not the same. So what we've done was our own setup, and we used the components. We took the block diagram of the provided board by Infineon, and we created a similar board with a few different components. But the main part of the board, which was the DC-DC converter, this is the part of the board which converts the energy, and it is responsible for obtaining the maximum power point of the panel, was exactly the same. That was our goal. Moreover, this helped us to debug and watch some physical process better, not only on a simulation. And that was an improvement I think we made here, because our hardware setup helped us to work faster and to see some issues and to troubleshoot them a lot faster, and it saved us so much time. We also increased the input capacitance because we wanted to make sure that the current we drive from the PV is continuous, because this leads to maximum power from the PV, because the converter has a mode where you need to stop taking power from the PV. This is not optimal because this power is lost, and we wanted to make sure that this power can be also obtained. So that's why we suggested and added bigger input capacitance. We also here suggest the addition of temperature sensors, which can help if you have a big array of PVs, not only one. You can detect if there are clouds and partial shading, and the algorithm can cover that and also find the maximum power. Well, that was our device flowchart. The flowchart is a type of diagram that shows the device behavior from the power up of the device to its shutdown. We suppose that there is no shutdown of device because we want to track the maximum power point continuously. And when our device is powered up, it needs all the peripherals of the microcontroller which are needed for the operation and for tracking the power point. Then we found the optimum mode for the converter, because the provided board by Infineon had a really, I would say, amazing topology of this DC converter, because this topology can operate in a buck boost mode, and the output voltage is not reversed. And this is a very big advantage of this schematic, because we can run it in both modes, buck and boost. And in boost mode, the stress on the components is bigger, but the power you can retrieve from the PV is also larger. So we decided to make it work. And we implemented mode switching, which can, this part of the algorithm can pick the better mode for working to obtain the maximum power. We also used a maximum power point algorithm, which we developed to keep this power point always to keep the power point of the panel. And this way we ensure that continuous in time we can run our power panel in this point. And once in 30 minutes, we decided to run a global maximum power point algorithm. Why is that needed? When you have an array of PVs, which is the real world example, you can have a few maximum power points. The characteristics, it does not look like a single PV, which was shown in the first presentation, but it looks like you may have some more power points, and only one of them is the global one, which is the maximum power from the panel. So we need to make a sweep of the characteristics of the PV array and find the most optimum power point. Also, we implemented a protection for the circuit and for the load, because you do not want to connect your phone, for example, to our system and to get blown up, or your power supply or your charger for something. So we created a protection for the output, for the input, because we do not want also to damage the panel. In case the protection is triggered, we shut down our device and wait for better conditions to turn it on again. So our proposed algorithm was very simple, incremental conductance. Firstly, we tried with perturb and observe, but we got a lot of oscillations of the power point, and we were not happy with that. So we decided to take a different approach. The incremental conductance, I will not bring you too much details, but the main idea behind the algorithm is the following. You can measure the current and the voltage of the PV, and based on the conductance change from the previous point you measured, you can determine whether you are on the left side of the slope or in the right side of the slope. And by doing so, we can make a decision whether we should increase the voltage of the PV or decrease it in order to obtain the maximum power point. It's very simple. I know it looks kind of complicated in the block diagram, but the main idea is that you measure the voltage and the current of the point. You know the voltage and the current of the previous working point, and by the difference in conductance, you can know whether you're on the left side, on the right side of the slope, and take a decision what to do with the voltage reference. We also implemented a variable step because when you are too far away from the maximum power point, you want to increase the voltage faster. And when you are really close to the power point, you want to increase the voltage with a very small steps because you do not want to have big oscillations which will make the power point unstable. And that was our concept here. Also, we had a global MPT algorithm, which I know here looks always complicated, but the idea is simple. We choose a working mode, which is buck, and we set the voltage of the PV to its minimum. And then we set this power point, wait some time to obtain the results, to measure the results, because we were also dealing with some noise. But our solution to the noise were some software filtering, which we created. And once the point is obtained, we store the information for this point. For example, we store the voltage, the power, and the mode in which it was obtained. We also store if this power point is valid, because some power points may trigger the output protection. This is not good, and these power points are not really power points you want to have in your system. So we just do not find them, and we do this, and we increment the input voltage with a few with our step, and we repeat this until we reach the maximum of the power point. After that, we switch the mode to the boost and do the same. After this process is completed, we can find the point which has maximum power. We know the mode, we know the voltage, and whether it's a valid power point. And this is our global MPT algorithm. So thank you all. The most valuable part of the challenge was to work on it, to have a chance to work on it. And what we liked the most was that our device, we created it, we ran it with a real PV, and we got, I think, outstanding results. So thank you all for the opportunity and for listening to me. Thank you.
Thanks a lot. Thanks for that. And with that, I would hand over to Passau.
Yeah, thanks. We would be ready. Everything should work. I hope.
Ja. Wir hören euch, wir sehen euch.
Okay, screen share should also be there.
Yes.
Okay, so we had to, after the other presentations, we did some last-minute changes to our one. This is to better convey the status of our build-up and our setup, because I think most of us didn't have much electronic engineering background. So, will you work? Yeah. So most problems we had until now were part of no electrical engineering knowledge. So we did a lot of read up on how the whole stuff works at all, and also how power PV cells operate, because that's a bit different to normal batteries or something like that. Where we also had not really fitting hardware for power supply load and so on. That's solved itself, but each took some weeks. So our first setup that actually worked used 90 meters of telephone wire with around 9 ohm resistance, because that could handle the power output, because the small resistors had release their magic smoke when we tried to use them. Yeah, that's whole setup a bit messy. Nowadays, or in the end, we have we got a variable load, which allowed us to ditch the whole resistor thing and the telephone wire. And yeah, this also got a small solar panel for testing, which is really secretly held out of the window. We also, until now, did some basic simulations regarding finding maximum power point. So the plan for the next weeks or so until the end of semester is to actually get the algorithm to the microcontroller, test it if we have sunny conditions, and then write a nice report for the grading and so on. And then I think we all went out of the project with way more knowledge of electrical engineering, and some of us are glad if they don't need to touch hardware in the next few weeks again after the end of the project. But well, that's from our side.
Very good. Thanks a lot. So you see, thanks also to you for giving us that feedback. Yeah, I just can conclude in that sense. I think we had now really a lot of teams working in that area.
Andreas, we
Yeah.
have 2 teams actually from Passau.
Oh,
I
sorry.
don't know if you saw the email. Obviously not. But there's a second presentation.
Oh, sorry. I was not. I didn't know them. Please go ahead.
Thank you very much. I'm Lóránt Meszlényi from the Passau University. And I'm actually not a group, but a one-man show. So I will show now my results. First, I also get started with understanding how the entire thing works and figuring out the buck boost converters, playing around with duty cycles in Dave ID. And then I figured out that at least I think that I need actually 3 modes of operation: a buck mode, a buck boost mode with synchronous PWM mode, and a boost mode, depending on the actual voltages, because you know the DC boost voltage can also vary a lot. And following this idea, I set some peripherals, try to implement something. The results are actually most of the things works now. ADC works most of the time, and I think I figured out by now that it is because of the noise why it doesn't work, and started to implement my perturb and optimize algorithm. And it's yes, what doesn't work is actually what I did not achieve now is filtering the ADC output and do some efficiency measurements on my device. I had also some challenges because my debugger didn't work at the beginning. I cannot read any values over the serial port, and there are also no test points on the PCB, which makes testing really hard. So you cannot just drop the oscilloscope probe somewhere. You have to actually think about how it would work in actual hardware. This is from my side. Thank you very much.
Thanks a lot. So apologies from my side that I now did not take you into account. Yeah, to summarize, I think it was a very successful challenge. We had a lot of interesting teams. I think the learning effect and the interaction also was really great for the different people. And therefore, a big thanks from my side that we had so much members participating here in our challenge. And I'm looking forward to really team up and work with all of them in future as well. Thanks a lot.
Thank you, Andreas. And you had a very widespread team setup, I think. Which of the solution can I buy now?
They are these. You have to go to all the different university teams and see to negotiate what is then the optimum for you.
Okay, perfect.
Start in Vienna and then work further towards Passau, Zagreb, and Sofia.
All beautiful locations. We are going to switch back to German in the main channel now. So everybody who was on the main channel for the English channel, please switch back to English, where Ursula Fischer is translating. Danke an die Infineon für diese Challenge. Ich glaube, da gibt es noch großes Interesse. Ich wurde gerade darüber aufgeklärt, dass ich jetzt an die Universitäten gehen kann, um diese Lösungen auch zu bekommen.